I want to talk just a little bit about graph modeling. So when we talk about graphs, they are a very general way of expressing a whole lot of problems. And so I'm going to show you how some dynamic programming problems even can be phrased as graph problems. And we'll hopefully get to that today. But often the issue that we face is not just coding up an algorithm. It's not just identifying, okay, how do I apply this algorithm to something that is obviously a graph? A lot of times the problem is, how do I actually turn the problem into a graph problem? Like, how do I recognize that what I have is a graph problem? And so this all comes down to what's called graph modeling. It means taking a problem and identifying it as a graph and figuring out what the edges should be, and then what algorithm do you need to use in order to solve problems in that domain. Okay, and it's not always obvious. There's many times that you can phrase something as a graph that it's not immediately obvious that it is a graph. Okay, so one way that this works, one way that it works in general, is as a way of doing state transitions. Okay, and so basically the idea here is that states are nodes and the transitions are edges. And you'll often see, if you take operating systems or something, you should learn about state diagrams. And you should learn about how you process state diagrams. But the key is, anytime that you can identify anything that has a state, and when we've talked about dynamic programming problems in the past, we're usually talking about state. That's like the specific parameters for a DP solution. Okay, so any of those state problems you can usually phrase as a type of graph problem, or at least set it up with a graph structure. And just recognizing how to do that is useful. Okay, so I'm going to give you an example here. We'll run through an example that might not immediately seem obvious, or it might not seem obvious how you set it up as a graph, but it's one where if you think about things in terms of state, it's okay. Now the examples I'm going to pull today are mainly ones that I got from the book, and because they're excellent examples of these ideas. So if any of you are proactive and have read the book, you might have seen these before. Okay, so let's go with the first one. And so this is going to be a car fuel problem. And so the idea here is you have a set of cities with roads between some pairs. Each road will require some number of gallons of fuel. Okay. You can buy fuel in each city for a price that varies by city. And then the question is, what is the cheapest way to get from a start to a goal? Okay, so think about the problem here for a minute. We've got some set of cities. We've got roads that go between them. Okay, each of those roads takes some number of gallons, depending on whatever conditions there are. So maybe there's one here. Maybe this takes 4 gallons, and this one takes 3 gallons, and this one takes 8 gallons. And this takes 3, and this takes I don't know. This takes 9. Okay. And then there's going to be a cost associated with the gas in each place. Okay. And I don't know that these numbers are going to be good, but it doesn't really matter for setting up the graph. So maybe this one, in this first city is going to cost, I don't know, 4 units of gas per gallon. And this one over here is going to cost 5 per gallon. And this one over here is going to cost 3 per gallon. And this one down here might cost 2 per gallon. Okay, so fuel has different prices. And the question is, what's the cheapest way to get from a start to an endpoint? So if we say that this first one is the start and this one down here is the goal, okay, you can see you've basically got 3 routes you can go. So if I sort of go across the top, I could buy 4 gallons there, in there. Oh, and I should have mentioned one other thing. You have a fuel tank capacity. You have a maximum capacity. So, for instance, if I wanted to go from the start to the goal across the top, I could buy, let's say that my capacity is 6 gallons. Okay, and if I am going to follow the green path here, then the cheapest route for me to go along the green path would be to buy 6 gallons at the beginning at $4 each, and then that would get me to the next node. So it would get me from here to here, and I would have 2 gallons left, and I'd need to buy 1 more gallon at $5, and then that would get me down to the goal, right? So I'd have 6 times 4 plus 1 times 5 would be $25 with that route. Make sense? Okay, another one would be, pretend I could go this route. Well, guess what? That takes 8. Maybe I shouldn't have done 8. Let's change this 9 down here, by the way, to a 6. Okay, first of all, that 8 is too long. It's bigger than my fuel tank capacity of 6, so it's not really possible. But if it were possible, it would cost me $32 even then, because I'd have to buy gas at $4. Okay, if I took this bottommost route, I would probably buy, so this is the purple route. I would buy 3 gallons at $4, so that would be $12, and then buy 6 more here, so that would be 18, and that would come to 30 total. Okay, so the green route turns out to be the best route. Okay, so that's the type of problem you have. So if you run into a situation like this, the question is, how can I write that as a graph problem? Because you look at that and you'd say, yeah, that's sort of a shortest path, right? Kind of. So let me ask, does anyone have an idea of how you would set this up as a graph problem, a simple graph problem that we know how to solve? No one here is volunteering. Anyone online want to say, I know, in the chat? No one's volunteering that they know. So let me show you. Maybe gallons times price is the edge. Okay, that's a great idea. I was hoping someone would guess something like that. And so that is a tempting way to do it. Gallons times price along the edge seems like it would be a good idea, but it's actually not. And the problem is, like in that first example there of 25, is I can buy more gallons of gas at one location and have extra fuel left, and I don't necessarily have to buy it at every location along. Okay, so what you will do instead is, I'm going to label these things A, B, C, and D. Okay, is I am instead going to turn this into a state diagram. Okay, so I will try to represent things as the state. In other words, what's the condition that I'm in at any point in time? And so the state is going to have 2 parts to it. It's going to say the city that I'm in and how much fuel I have. Okay? Right? And so in this example up here, my starting position is I'm in city A with no fuel in the tank. And when I end, I want to end in city D with 0 fuel in the tank, because if I have any fuel there, it was a waste, right? I wasted fuel. So I'm wanting to go from A0 to D0. Okay, and so we will set this up, and you can write it kind of like this. I can have A, B, C, and D, and I will have nodes. Okay, so in this case, I have a node for each city and for each fuel level. So this is going to be the fuel level. How many gallons are in the tank? 6, 5, 4, 3, 2, 1, 0. Okay, and now I need to put my edges in the graph. And the edges are going to be the cost from one node to another. So if I go up here, my fuel at node A cost 4. If I put edges like that, okay, I have edges like that they go up. What is the weight per edge? What does it take for me to go from 0 gallons to 1 gallon? Yeah, the cost. So in this case, that was 4. Okay, so for A, this is 4. For B, the gas costs $5 a gallon. Let's see, for C, it costs 3, and for D, it costs 2. Although truthfully, we don't really need to worry about D since that's where we end up. Okay, does that make sense? Okay, the other thing we can do is we can drive from one city to the next. Okay, and so I'll draw these edges in blue. Driving from one city to the next, notice that if I go from A to B, that's a distance of 4. And so that's going to be an edge that goes from, say, 6 gallons down to 2 gallons, or from 5 gallons down to 1 gallon, or from 4 gallons down to 0 gallons. And how much does it cost us? Like, how much money do we have to pay to drive? Nothing, right? There's no cost. So each of those is going to have a weight of 0 to them. Okay, going from B to C is not possible. Going from B to D is a distance of 3. So I can go 1, 2, 3. Okay, those are the edges from B to D. We also have edges from A to C that are distance 3. So there, that's A to C. And then we have C to D, which is 6. So actually there's just that 1. And we also would have had A to D, but even going up from 6, it would have gone to -2. So that's not really possible. Okay, so notice each edge takes us from state to the next state. So all of those edges are a state transition in this diagram. And so our goal is to go from the starting point down here to the ending point right here and do it with the shortest path possible. Okay, so in the end, we just run a single source shortest path. We run Dijkstra's algorithm on this graph, where we've instead modeled the states instead of the actual like distances or roads or anything like that directly. Okay, I think that's kind of cool. Like, isn't that cool? Yeah, okay, yes, I got some other heads here. I think that's kind of a neat way to look at the graph. So this type of problem where you have one thing, you often will need to think about how can I represent the state that I'm in, and then what are the transitions from that state? And so these changes, they could be something like here, which is the amount of fuel. It could have to do with time. It could have to do with resources that you're using or not using. There's a lot of different ways that you can like measure what a state involves. It could have different aspects to it. But being able to sort of write a problem in a graph form like this, even if it seems like a simple graph, like this graph looks a whole lot more complicated than that one, right? I mean, this original one up here, that doesn't look like such a bad graph. I mean, it's only got 4 nodes and 5 edges, and now we've got a whole bunch of nodes and a whole bunch of edges along the way. So yeah, you get the idea. Okay, and so by the way, in this case, the shortest path was to go believe, up to here, yeah, all the way up to the top, then to there, oh, sorry, then to there, and then to there, and then to there. Well, I did something wrong. I don't know. Oh, A to B, sorry, B to C, B to C, and then I've already forgotten it. I messed it all up. A to B, B to D. Oh, I never, yeah, A to B, B to D. I should have gotten to this one right here. I should have gone there, followed that edge, and then up, and then followed it down. Sorry, I'm going to undo all that real quick so that I can draw this. Sorry about that. Okay, so the idea, again, is I would go all the way up. I'd buy 6 gallons here. I would travel to B, which would leave me with 2 gallons. I would buy a gallon there, and then I would go to D. So that turns out to be the shortest path along the way. Okay, through that graph. But that's probably not obvious. I mean, you don't just look at that graph and immediately say, oh, that's the shortest path. Okay. So that's one way that you can modify your graphs to fit into a graph model. Another thing that you'll see come up quite a bit is you'll see things that have vertex weights. Okay, and so a vertex weight is where there is a cost for going to or through a vertex. Okay, and this, at least this trick that is used is something that it applies more when you have it's easier to see this when you have a directed graph than when you have an undirected graph. It doesn't work quite the same way. But the idea is if I have a cost here that's cost C, and I have some incoming edges, so I'll write incoming edges in red, and I've got some outgoing edges, and I'll put those in blue. Okay, and there's some cost associated with going through that graph. And I think they probably teach this to you in 411, right? Yeah, some of you are nodding. So the idea is you split your node into 2, and you have your incoming edge and your outgoing edge, and you put the cost on that edge. So all of my incoming ones would come here, and all of my outgoing ones would go from here. Okay, and so if you imagine that you have any path that goes through that node, okay, any path that was going to go through the node, it has to come in here and then go through there. So it's going to come in on some path and go out on some path. And so it accumulates the weight of that edge. Okay, so if you're wanting to do like a shortest path algorithm and you're given something in addition to the weight per edge, you're given a weight per vertex, you can always split the vertices in 2 and just keep your incoming and your outgoing ones like that. That makes sense? Okay, so that's, I mean, it's a pretty straightforward trick, but if you haven't seen it before, it can be really confusing on how to handle vertex weights and process them along the way. But it's not actually very difficult to modify your graph to do that. Now notice, you double the number of nodes in your graph, okay? And you add that many more, like however many vertices there are, you add that many more edges to the graph. So you expand the graph. Both of these things are ways that you can expand the graph quite a bit. Okay, and okay, I'm gonna go very quickly. I'm not gonna go through all the details of this, but I will mention that there's special types of graphs. One of the most common ones that we care about is a directed acyclic graph, or a DAG. And the thing is, if you have a directed acyclic graph, that really simplifies a lot of the processes that you have, a lot of the algorithms that you can run on there. And so the way to think about it is if you have a DAG, then if you run your topological sort, okay, which we've talked about before, was a problem on your previous problem set. So you run topological sort, that's going to give you an order to visit the nodes. And then this order really simplifies a lot of other problems. For example, For example, if you do a single source shortest path, Dijkstra's algorithm, you can just do it in the order of those nodes. You can do it in the topological sort order from your starting point. And if you do that, you don't ever have to worry about like going back and re-relaxing things. You just relax each edge in topological sort order and you're done. Okay? There's no worrying about going back. It's a asymptotically simpler solution. Okay, so there's a lot of cases where that comes up. But probably the most interesting aspect of this is that I would say most dynamic programming problems. They can be turned into a problem on a DAG. Okay, so with what I was talking about with states before, if you think of your dynamic programming states as nodes in the graph, and you think about the transition from one state to the next, normally when we write things, if you remember when we do DP, we do some DP of A, B. Okay, these are like the parameters. And just like before, just like we had up here, we had like the parameters here. Each of those things basically gets turned into a node. And then the edges in your dynamic programming are when you do something like, you take the minimum of, DP of blah, 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 DP of something else, DP of something else. Each of these is an edge to a new node. Okay, and if there's some cost associated with doing this, then that's something that you can build in potentially, depending on how it's set up, you can potentially build that into the individual vertex node weight, just like we talked about here. Okay, so a combination of those two things that I just mentioned allows you to transform a lot of dynamic programming problems into a graph problem. Now, it's not, in fact, usually it's more work to solve the graph problem, in my experience, but it sometimes is a more helpful way to think about it. And if you're really struggling with how to work something in a dynamic programming environment, putting it into a graph problem can sometimes be simpler conceptually to think about it. Okay, in both cases, you still have states. Your states are your nodes, and the transitions between states are the edges. So I'm going to give one example of this. We could do the same thing with knapsack, but I'll show you like the coin change. Okay, so if you remember, the coin change problem is when you have a certain amount of money. So you have money M, and you have coin values, C1, C2, C3, and so on, right? Okay, and you want to find how few coins are there. Okay, so if I want to write this now as a graph problem, we've talked about the DP example. I have a video about it. I would encourage you to watch the video of it if you're like having difficulty with dynamic programming, because it's like one of the classic problems. But here's how you can describe it in a graph format. You create nodes that are M, the amount of money that you have that you need to make change for. Okay, so in this case, like 0, 1, 2, 3, 4, 5, 6, 7. Okay, so maybe we have up to 7 units of change. Okay, and you create an edge. So you create a node for each value. You create an edge for each coin value. From each node. Okay, so say that the coins have values 1, 3, and 4 as an example. Okay, what that means is that I have an edge that will get me back 1, it will get me back 3, and I'll do that in green. 1, 2, 3. And I have one that will get me back 4. Right? And I'm going to have this for every single one of them. I'm going to have one that goes back 1. I'm going to have one that goes back 3. And I'm going to have one that goes back 4. Okay, so there's my graph. I make the graph. Notice this is not something, I don't read this graph in from a file. I don't like read in my nodes and edges and things like you're used to for graph problems. You have to form the graph yourself, including figuring out these are where the edges should be. But you can do that procedurally, right? You can write a procedure that generates all these edges and nodes for you, okay, for the problem. And then what you're left with is you want the shortest path. And these are all, notice it's an unweighted graph. So how do we get shortest path on an unweighted graph? BFS, yep. So you just perform BFS. Okay, so the coin change problem where we described it as a dynamic programming problem and all of that sort of stuff, and we had these different parameters, we can phrase the whole thing as a directed acyclic graph where we're just applying a graph algorithm. Now, sometimes it's really difficult to do this. It's not always possible, but this is like a simple example. And I bet for most of you, you look at this and you say, whoa, that's way easier than the dynamic programming, especially if you're not like comfortable with it yet. This might look easier to you. And maybe in this case it is. Usually this is not going to be easier, but it is another way of looking at these problems. So keep that in mind. So we've got just a couple of minutes. I'm not going to have time to go through everything, but I want to briefly introduce the idea of max flow to you because that's going to be the topic for this week. You will want to watch the video when I finally get it posted late tonight. Wait, question first, yeah. That's right, yeah. So the question was, do you count each edge as weight 1? And the answer is yes. So like a BFS just says how many like steps away are you? So that would be an example here. That it's the same as counting everything as weight 1. Okay, so just to introduce the idea of max flow to you. The idea of max flow in general terms is you have a source and you have a sink. And your source is producing stuff, okay? When I was first introduced to this, it was oil wells and pipelines. Okay, so you have oil producers and you have a refinery that you need to get everything to, and you have pipelines that go along the way. And there might be junction points, and they might be able to send stuff to other parts of the pipeline, but each one of these has some capacity to it. 8, 4, 6, 2 and 2, 3 and 5, 4, 1, 9, 6. Okay, so there's some. So just those. So the question is, if I'm producing oil here and the maximum amount I can send through any pipeline is that amount that's listed right there, and these can be directed edges or they can be undirected edges. Depends on the problem. Okay, but let's just say they're directed for the moment because this is kind of a straightforward one. So they're directed edges. How much oil could I get from the source to the sink? And you can imagine, okay, I can get like, I can send 8 here, and so maybe 6, 5. So I can get 5 units on the red path because 5 was the least I could get on this, was the most I could send there. So I got 5 units on the red path. And then if I take a blue path here, I might be able to send 3 here and then 2 here. There's still 2 there and 2 there. So I was able to get 2 on the blue path. So I can get 7 so far that way. The question is, how many can I get through this graph? And this is the max flow problem. And one of the things that's interesting about it is there are a lot of other problems, a lot of very general problems that you can phrase and rewrite as max flow problems. So I'm going to give you an example of another problem that you could write as a max flow problem. As far as how to solve this, that's what's going to be in the other video that comes later. But I'll give you an example. This is one of my favorite ones. It's eating pizza. Okay, so you have a bunch of pizzas of various types. And then you have people who want some number of slices. Okay, and they have a list of pizzas they will eat. Okay, so like for me, I don't eat pizzas with vegetables on them. Ugh. Okay, so I would not eat those, but I would eat all the other pizzas. Okay, and other people might be the exact opposite. They only eat things that have vegetables. Maybe someone will only eat pepperoni pizzas and whatever. Okay, and so the question is, how many slices will get eaten? Or you could think of it as, are there enough pizzas to satisfy everyone? Okay, because you might say, oh, well, if I give you pepperoni, then that person who could only eat pepperoni can't eat it. But if I give them the pepperoni, then I could give you the supreme pizza and everything would work out. Okay. How many slices will get eaten? Or basically, can you feed everyone? Okay, and that might not immediately look like it could be a max flow problem, but it is one that you can phrase that way. And so the idea here would be you would have a source that is the source of all pizza eating, I guess, and you would have people here, okay, and you would have pizzas here, okay. And so the way to think of it is, if I take a path from the source to a person, to a pizza, and to the sink, it means that that person is eating some number of pizza of some number this person right here is eating some number of this type of pizza. Okay, however much flow there is along that path is the way to think of it. Okay, and so now I need to come up with the edge weights and which edges to include. Well, for one thing, you can include edges just for the pizzas that individuals are likely to be willing to eat. Okay, so there's only an edge between a person and a pizza if the person is willing to eat that pizza. And then from your source, you have the maximum number of pieces that each person wants. So maybe this person wants 3, this one wants 1, these want 2, this person is starving and wants 5, this person is really hungry and wants 8 pieces of pizza. Okay, so you have some number of pieces that they want, and then you have the pizzas themselves, and there's probably a limit on how many slices are in each one. So you can't have more than 8 of any one of those, right? Okay, now there's not really any limit between the people and how many of any one pizza they can eat. So between this relationship here in the middle, there's not very much there. There's nothing to like limit how many, the limitation is how many pieces do they want total, not how many of any one particular type. Okay, maybe if you did have something that said each person wants no more than one of the same type, then each of these might only have weight 1. Okay, but assuming you don't have a limitation like this, you can make this kind of your maximum weight, which in this case might be 8. Okay, because you'll never even get to that point, but this is like an upper limit on what's there. So the flow level, like the capacity can always be larger than you need. Okay, so you can think of it as infinity or 8 or whatever you want along the way, but it's a plenty large value for all of the ones. Okay, so that's how you can, as a flow problem. The idea is the more flow you can put through here, basically anything that can flow from the source to the sink means pizza getting eaten by some person of a type that they like. So a path that goes through will do that for them. Okay, and so when you encounter max flow problems, which are going to be the problems for next week's class, you will need to be able to model the graphs appropriately and figure out how much flow you can get through them. But kind of the key part of it I mean, it's one thing to implement the algorithm itself. That's a challenge. Okay, this is a trickier algorithm than some. Okay, but once you implement that, kind of the core part is how do I model the problem as a max flow problem? So I wanted to kind of introduce that along the same theme as what we had before with other types of problems that we have along the way in graphs. Okay, any last questions? Yeah. In this week's problem set, the one you're working on right now, no. There's no max flow this week. This will be the ones you get next week, will be max flow problems. Or related to max flow, at least. Okay. Well, in that case, have a good weekend. I'll see you next Monday. Again, I will post the problem set. It'll come up on Friday. And I will announce when my office hours are for Friday, and I'll ask Drew and Presley to note whether or not they're having them on Friday or if they're at different times or anything like that. Okay. Bye.